Hey guys, welcome to the last video from chapter 11. What we're going to talk about in this video is heating curves, and then we're going to talk about phase diagrams. So it's going to tie into everything we've been talking about with the boiling and vaporizing and melting. We're just going to look at it from a slightly different angle. So let's just go back and review what boiling is. We'll talk about what melting is, and then we'll tie this into a heating curve. So boiling, remember, is when we're going from a liquid to a gas. And now that we know a little bit more about vaporization and vapor pressure, I can give you a slightly more sophisticated definition. So boiling is going to be the temperature when a liquid reaches the point where vapor pressure is the same as external pressure. So what this means is once we reach the boiling point, it's not just the particles that are at the surface that are available to become a gas. When we reach the boiling point, now all of the particles are available to become a gas. So there's enough energy in that solution or in that liquid so that we can pick any of the molecules and they can become a gas. That's why we see these bubbles forming all around a liquid. So that's going to be the boiling point. And remember, thinking about intermolecular forces, we're still breaking those interactions between a liquid particle, freeing them up to become a gas. Melting. So melting is very similar to boiling in that we're breaking intermolecular forces. But here we're going from melting solid to a liquid, so thinking ice to liquid water. So melting is when molecules have enough thermal energy to overcome the intermolecular forces that are holding those molecules in the stationary positions. So particles are still packed very, very closely together. In a solid, they're in a stationary position. They can vibrate, oscillate in place. When they go from a solid to a liquid, now they have the freedom to kind of slip and slide past each other. So we have enough thermal energy to overcome the stationary intermolecular forces, but there's still other ones that are there holding those together. Okay. The next thing that we're going to look at is a heating curve. So I'm going to display the entire heating curve. It's going to be a really busy slide. We're going to spend lots of time on this slide breaking down the different parts and what we need to know about it. So here's our heating curve for water. Okay. One of the things that we notice right away is there's 5 labeled places on here. So 1 is right here going up, 2 is flat, 3 going up, 4 is flat, 5 going up. Okay, so we see 5 different positions. We see our different phase changes. So right here is our melting point. Right here is our boiling point. So those are 2 of our phase changes that we've talked about. Right now, this heating curve, as I go from left to right, we're adding heat to the system. As I go from the bottom to the top, the temperature of that system is going up. So as we're moving from left to right, heat is increasing. As we move bottom to top, temperature is increasing. Okay, so let's start breaking this down. In this first area here, what we see is something that we would expect to see. So as heat is added to the system, so we put it on a hot plate, we put it over a fire, whatever we do to it. As heat is added to the system, what happens? Temperature goes up. Heat is added, temperature goes up. Heat is added, temperature goes up. Okay? So in this first increase here, we see what we would expect to happen. Our first change in this curve, so our first flat line here happens in position 2, and it also happens to be right at 0 degrees Celsius. What do we know is important about 0 degrees Celsius? Well, 0 degrees Celsius is where water freezes. So if we were coming down the curve, we hit 0, we would have freezing water. Or if we're increasing the temperature at 0 degrees Celsius, we would go from a solid to a liquid. So 0 degrees Celsius is a really important position for us. What we notice here is a flat line. So what does this flat line tell us? I add heat, but the temperature doesn't change. And then I add some more heat and the temperature doesn't change. And I add some more heat and the temperature doesn't change. So we're adding energy into the system, but I don't see a change in temperature. So if I'm adding energy into the system, where is it going? What's it doing? What is that heat doing? Okay. So it's not changing the temperature. The temperature is remaining constant. So the energy that we're putting into the system is being used to break up those intermolecular forces. So during this flat line, all of the energy that we're putting into the system is going to breaking those intermolecular forces, breaking London dispersion, breaking dipole-dipole, breaking hydrogen bonding. So it's breaking up all those intermolecular forces, okay? During this flat line, we don't typically think of phase changes this way, but during this flat line, we're going to have two different phases present. So during this flat line, we're going to have solid water present, and during this flat line, we're going to have liquid water present, okay? So both states are present. And as we move left to right, we can see that gradual changeover. So right here, when I hit this dot, we're going to have most of our sample is going to be solid ice. Some of it's going to be liquid. We add some heat, a little bit more becomes liquid. We add some heat, a little bit more becomes liquid. Add some heat, a little bit more becomes liquid. At this second dot right here, that's where we have completed our phase change. So now all of the solid has become a liquid, and we get into our third point on the curve. So once it's all become a liquid, then we add heat, temperature goes up, add heat, temperature goes up, add heat, temperature goes up. Okay? So this flat line right here is our phase change. Phase changes happen at a constant temperature, and we have both phases present here. Okay, so we heat it up, heat it up, heat it up, heat it up, and then we come to another flat line. So that tells me we're coming to another phase change. So the next phase change that we see here would be the vaporization, the boiling point. So during this phase change, we're going to go from liquid to a gas. So again, add heat, temperature doesn't change, add heat, temperature doesn't change, add heat, temperature doesn't change. And notice this phase change is right where we expect it to be at 100 degrees Celsius. So what's going on during this flat line? Where is that energy going? Well, again, the energy is going to breaking up the intermolecular forces. So getting rid of those hydrogen bonds, getting rid of those dipole-dipole, freeing up these molecules to go from a gas and escape as a liquid, okay? So over here, we would have mostly liquid, a little bit of gas, add heat, more gas, add heat, more gas, add heat, more gas, so on and so forth, till we get to this point right here. Once we've reached this point, our phase change is over. Our entire sample is now a gas, and we add heat, temperature goes up, add heat, temperature goes up. So just to summarize this heating curve for water, we've got 3 sections where we add heat and the temperature goes up. We've got 2 sections, section 2 and section 4, that are flat lines, and that's where we see our phase changes. Okay. Here, this just shows us a picture of what the molecules look like. So this would be for section 1. We're adding heat, temperature goes up, adding heat, temperature goes up. So essentially the ice is warming up is what's happening here. During our phase change, here we see some of them have become a liquid. We still see a little bit of the solid ice. So we've got 2 phases. It's in the process of melting. Here in the third section, we've got all liquid water, and that liquid water is warming up, it's heating up. Step 4 is our next phase change. We see some of it is still liquid water, some of it is gas, vapor. And then once all of it becomes gas vapor, and then we just see steam, and we continue to heat up that steam. All right. So this tells us about this temperature. So how does temperature affect the phase changes? So we've talked about how temperature affects phase changes basically all through this chapter. But I can't exit the chapter without at least acknowledging that there is another factor at play here. So not only can we increase and decrease heat to induce phase changes, pressure is also something that we need to consider. It's also a factor that affects these phase changes. So the way that we see pressure as affecting these phase changes is in phase diagrams. So a phase diagram is going to show us a lot of information. So on a phase diagram, we're going to see first the 3 phases that a substance might be in. So this is the phase diagram for water. We've got solid water, we've got liquid water, and we've got gas. So solid, liquids, and gases. Okay. We're also going to see the phase changes as lines. So when we go from a solid to a liquid, this is going to be the melting line. This is where we would see that ice would become a liquid water. They call it the fusion, the fancy word for fusion. They're actually thinking about the other way. So liquid fusing together into a solid. Here we see the vaporization curve, so going from a liquid to a gas. So during this line right here, that's where we would see that it's going from a liquid releasing into a gas. And then this line right here, it's not something we talked about this chapter, but we've talked about in the past, sublimation curve. So if something goes straight from a solid to a gas, it happens. That's called sublimation. So that's the process that's happening on this curve. Okay. The other thing we see is both things that are at play. So down here we see temperature. So going from left to right, temperature increases. And then here we see our pressure. So going from bottom up to the top, our pressure would increase as well. So that's all review. A few new places that we see on this phase diagram for water. We see this triple point here. So at the triple point, we will see all 3 phases present. There's some really cool videos on YouTube, so you can Google triple point and watch some pretty cool videos where you'll see the solid, the liquid, and the gas all present within a beaker. So pretty cool videos there. And then the critical point is when liquids and gases no longer have a defined place. We've had something called a supercritical fluid. So it's got gas and liquid properties. So it's called a supercritical fluid. And again, some really cool videos on YouTube about supercritical fluids. One of the really easy, fun facts about supercritical fluids, a place that they're used that we can actually kind of understand, is they're used to decaffeinate coffee, and it's also used to extract the hops that we use to make beers. So we heat up, let's say, a caffeinated beverage, for example, and then we find a molecule that latches onto the caffeine. Then we condense that back down into a liquid, but the caffeine evaporates off. So that's one way we use supercritical fluids is to decaffeinate coffee. So pretty cool, fun little factoid there. Okay. So how do we read these phase diagrams? So what we see here is they've marked 760 torr, or 1 atm is the same thing here. So this would be the pressure just at sea level, right? So if I were to take the temperature inside of this classroom, it would be at essentially 1 atm. So this is atmospheric pressure at sea level. Down here, we see our temperature. So if I would match up the temperature at sea level with 0 degrees Celsius, what I see is exactly what I would expect to see at 0 degrees Celsius, 1 atm. That's going to be our melting point right here. So anything above 0 degrees Celsius, that would be liquid water. Anything below 0 degrees Celsius, that water would be ice. It would be a solid. Okay. Moving on, I see that vaporization curve, and not surprisingly at all, that happens at 100 degrees Celsius. So anything below 100 degrees Celsius, that water would be liquid. Anything above 100 degrees Celsius, that water would be a gas. Okay. In order to get to these crazy sublimation points or triple point or supercritical fluid, what we're going to have to do here is manipulate the pressure as well as the temperature. So in order to get up to this supercritical fluid, not only would we have to dramatically increase the temperature, but we'd also have to have a pressurized system. We'd have to significantly increase the pressure to get to something crazy like the supercritical fluid. Or for the triple point, for water, for example, we would have to lower the pressure and then also keep that temperature really close to 0. So that's how pressure and temperature affect these phase changes. Okay. Here is the video for triple point. So if you want to go ahead and open up the PowerPoint that I have and click on this video, it's a pretty cool video for the triple point. So reading phase diagrams, I can ask you a few questions. I'm going to show you an example in just a minute. But I can ask you something like, at 25 degrees Celsius, what state, and 1 atm, what state is this substance in? And so you would say 1 atm, 25 degrees Celsius, we would be at the liquid state. I could say something like, where's the triple point? And you would say at 0.006 atm and 0.01 degrees Celsius. So just being able to relate the pressure, the temperature, and different points on a phase diagram. Okay. Before we dive into an example, I just want to look at the phase diagram for carbon dioxide, because I think it's kind of a fun way to tie in what we observe and then what we are learning. So if you think about carbon dioxide, if you've ever experienced dry ice, and if you haven't, we will get to in lab in a few weeks, so you'll get to see dry ice firsthand. But if you ever have any experience with dry ice is just the solid form of carbon dioxide. Okay? Why is dry ice called dry ice? Well, dry ice never goes into the liquid phase. So dry ice is solid carbon dioxide, and it sublimes straight into gas carbon dioxide. So dry ice never feels wet or never gets wet because it never enters the liquid phase. If we look at the phase diagram for carbon dioxide, we'll see the same thing at 1 atm. So at 1 atm of pressure, we see that carbon dioxide is a solid, and boom, it goes straight into a gas. It doesn't enter the liquid phase until we increase the temperature to 5.1 or above. Okay. So in order to get carbon dioxide to become liquid carbon dioxide, we'd have to significantly increase the pressure in order to see a liquid carbon dioxide. So dry ice is just solid carbon dioxide going straight to gas, and that happens at 1 atm of pressure. Okay. So here's a great example. I'm not going to go through all these because I think you guys will catch on pretty quickly. But here's a great example of how I could ask a question about phase diagrams. So consider the phase diagram of carbon dioxide shown below. What phase or phases are present at each of the following conditions? So I could say at 20 degrees Celsius and 72.9 ATM, what phase or phases are present? So you would find 20 degrees Celsius, which would be somewhere kind of right in here. Go up to 72 ATM, and this is 72 ATM. I kind of covered it up. So 72 ATM at 20 degrees Celsius, we would say it would be in the liquid phase. At negative 56.7 degrees Celsius, 5.1 ATM, what phase or phases are present? So that is at the triple point. The triple point is not a phase. The triple point is a point. So if I'm asking what phases are present, you would say all three, the solid, the liquid, and the gas are all present at negative 56.7 degrees Celsius and 1.5 ATM. Okay. So that ends our information for chapter 11. That's all the information that I have to share with you guys. You guys should be getting pretty close to finishing up this module and diving into homework, quizzes, and things like that. I hope you guys found this helpful.